Hey guys, welcome back. So today's video is all about building a DC electronics load, and I would like to provide you with all the information you need to know to not only build a DC electronics load but also to understand one. And if you watch other videos of mine, you may have already seen this one over here. Now this is a DC electronics load, a portable version. I actually built this because I had a prototype circuit and I didn't want to throw it away, so I decided to make a small portable version. However, in another video I will build a much bigger version that is capable of handling much more current, or rather much more power. Before we take a look inside of here, I would like to explain everything you need to know. And I think we start by taking a look into the datasheet of a MOSFET. In this case, I'm using an IRL540, and if we take a look into the datasheet, over here we have several graphs, and we have the typical output characteristic graphs. Doesn't matter if we choose the first one or the second one, they just are a bit different because of the change in junction temperature. But let's take a look at the 25 degrees Celsius diagram. So normally we want the MOSFET to operate in its ohmic or linear region on the left side over here to get a minimal voltage drop across the FET and therefore waste as little power as possible. But in this case, instead, we want to drive the MOSFET in its saturation region on the right to have as much power as possible wasted. And here we get high drain to source voltage drops. And that is very important. So this is how it works in the sense of the MOSFET, what we try to achieve. And this circuit over here does exactly that. Now if you search for DC electronics load on the internet, you will find a basic circuit, but this basic circuit does not seem to work, at least with my components. The basic circuit is exactly that, except there is no pull-down resistor on the gate of the MOSFET and no capacitor parallel to the MOSFET. The explanation for these two components is that the capacitor essentially dampens some oscillation happening between our load side plus and load side minus, and the resistor pulls down the gate of the MOSFET, so we actually have the MOSFET closing faster and more reliably. Without this, it just did not waste power for some reason. But you might not have to do that if you use different components. So let's go over the circuit and all the connections you have to make. First, we need a power source, and in my case I chose a 5 volt, I called it reference voltage, but that's not really reference voltage, that's a bit wrong. So we have 5 volt, we have the ground of the 5 volt supply, and a potentiometer. I chose a 10K potentiometer, and we have a potential divider, and the middle pin of our potentiometer is connected to the LM358. The output of the LM358 is then connected to the MOSFET over here, to the gate of the MOSFET. It's also important to note that the LM358 positive and negative, the negative is connected to ground, and I call it ground and V minus load because that's important. We have to connect power source ground, internal power source ground, to our V minus load side. That is a very important connection, and take a look at this. So I chose 2-pin connector for our internal power source, 2-pin connector for our load side. This is how it should look. All these points mean we have a connection between the lines, and if they do this over here, they just cross each other and there's no point. It means there is no electrical connection. So that's very important. It's sometimes a bit hard to understand. Some of these diagrams are not really well explained. Okay, so we have power, the internal power source, and I just said yes, we have the output going to gate of the MOSFET. Then I have, as I said, a pull-down resistor, a 10K pull-down resistor to our ground and V minus load. We have a here. So we have a load resistor in line with our MOSFET, and that's really important. This is to create a feedback, and the feedback connection is between our MOSFET and the load resistor. It goes directly into the op-amp. I just searched for the name. Okay, and then we have also a capacitor parallel to the MOSFET between connected to drain and source to dampen any oscillation that could happen between our plus side load and minus negative load side thingy. So yeah, and the size or the resistance of the load resistor really depends on what your internal voltage is and what the op-amp you're using can handle, but also what the maximum voltage you can supply to your MOSFET's gate. Essentially what happens is if we use a 0.1 ohm load resistor, for each 1 volt applied to the gate we would have 10 amp of a constant current. And if we use a 1 ohm load resistor over here, we would have 1 amp per 1 volt supplied to the MOSFET's gate. So that should help you choose which size. I think I did not forget anything. Yeah, that's everything about the circuit, all the connections and components. Now that I explained you all the components needed and how to connect them to each other, let's talk about how this circuit actually works. The op-amp over here works as a simple voltage comparator. And if our voltage reference provided by this potentiometer over here is higher than our feedback voltage provided by this point between our MOSFET and the load resistor, the output gets pulled high, which opens the gate of the MOSFET and makes the drain to source path conductive. Now current can flow through the 0.1 ohm load resistor. But by connecting a power source to our V plus load side and V minus load side, suddenly a voltage drop across the 0.1 ohm or load resistor occurs, which represents V feedback. If this voltage is higher than our V reference, the output of the op-amp over here gets pulled to ground and therefore closes the MOSFET. This decreases the current flow and a voltage drop. However, just before reaching 0 volt, V reference is already higher than V feedback, which again opens the gate. The circuit is now constantly oscillating. Okay, so now I explained to you everything you need to know about the basics, about how it works with the MOSFET and how the circuit works, what the most basic circuit is. We can now take a look at this thing over here. Now this thing I used in a few previous videos, and this is my first DC electronics load. And I built this one out of the prototype that I used to validate that the circuit I showed you actually works. I was unable to use my breadboard. I just constantly lost connection to different components, so I had to hard solder it together to see if it works or does not work. And when I was finished with the circuit, I just thought it would be a waste to throw the PCB away. And so I tried a few other things, and that's when this came together. Now, I have some enclosure where everything did fit inside. It's battery powered, and just let's go over it and see how it looks and take a look inside. And I will also give you an indication on what you need as a cooling solution. Sometimes when people do these projects, they tend to massively oversize their cooling, and they do not properly rate their electronics load, because it's not only a maximum current that can go through it, but a maximum power. Because what this thing does, it wastes the power going in, which is a combination. So you actually multiply the voltage and current going in, you waste that. This electrical energy gets converted into thermal energy, and you have to remove that much of power from the internal components. Most of the power is obviously wasted throughout the MOSFET, but also some power is wasted by the load resistor. So we have to get rid of this, and sometimes the cooling solution, or rather the heatsink, is massively oversized, and people tend to only rate for current. So you always have to make sure that not only your current going in does not exceed the limit of any component, but also the maximum power, the power dissipation does not exceed the maximum the components can handle. So this is also very important. And this small thing over here, depending on your ambient temperature, it can be used between 25 to 30 watt maximum power, and so power output. And this is quite remarkable, because when you take a look on the internet and search for DC electronics loads, there are DC electronics loads that are rated for 60 watt and have essentially a standard Intel heatsink sized cooler on them, and they are rated for 60 watt. But this thing has a much smaller heatsink inside, and still can handle, again, depending on ambient temperature, between 25 if it's cool, or no, between 30 watt maximum if cool ambient temperature, and 25 watt if your ambient temperature is higher. But enough of talking, let's take a look at it. So first you can see that I have a metal mesh over here, and there is a 5-volt fan underneath that pulls in air in over here, and we extract the air on these holes on either side. So that's my airflow path. Then we have these two switches. The upper switch is to turn on the unit. Right now the battery is disconnected. I prepared a few things. And the lower switch is to actually turn on the fan. Then we have a multi-turn potentiometer, so I can easily dial in the current I want to, or the power I want to waste, or rather the current. This is the current limit. We have a very simple volt and ammeter, a very cheap one, not very precise, but it's good enough. We have two, how are they called, banana plugs, not banana plugs, but these receptacles. And on the other side, a charging port for the single 18650 cell inside that delivers all the power for the internal electronics. And now we can crack this thing open, and here you can see a single cell in here, fits perfectly in. And with this aside, this is a slight problem, because you can't actually go too heavy on heat in here, because as you can see, the air passes through the heatsink over the cell. It's not perfect, but it's still good enough for the mentioned 25 to 30 watt of maximum power. Now this is connected with a 2-pin connector over here, and I have a boost converter that converts the one of the fans just started spinning. Okay, so it converts battery voltage to 5 volt. We have the multi-turn potentiometer over here, our two switches, again the volt and ammeter, the two banana plugs over here. The negative goes through this black cable directly into the volt and ammeter, and the red cable then goes into the circuit over here. And that's how it looks. I can't really remove it because everything is soldered together, but I hope you can still see it. And so here we have an LM358. We have the pull-down resistor. Under here, hope you can see it, is the IRL 540. I used some thermal paste. Let me just zoom in a bit more. I used some thermal paste for better thermal conductivity. The small brown dot over here, this is the capacitor that prevents oscillation between drain and source. And we have also there the load resistor. Now this PCB looks really weird, and yeah, so that's a prototype. That's how a prototype can end up looking. I had to just repair a few things. I did not only try the circuit, but I also tried a few other things afterwards, which did not work, and I had to get rid of them. That's what it ended up looking. However, as it is right now, it does work. And the cooling solution I also had to modify slightly over here, because this was a problem for the multi-turn potentiometer, but now everything fits together. And now the important part, I want to give you an indication on what you need. So obviously I use active cooling, and I have some Kapton tape over here, but on the back, Kapton tape on the back to prevent air coming this way out, because I want all the air to be forced in this direction. I try to force in air with this small fan into the channels. I want the air to stay in these channels for a bit longer, and just on the end to go out. And this fan sits directly above the IRL 540, so I hope I can create the maximum cooling this design can accomplish. Now the cooler, or the heatsink itself, is, let's see, 2.5 centimeters wide. It is 1.2 centimeters high. The fins themselves, if I remember correctly, are only approximately 9 millimeters, so 0.9 centimeters high. And the length is, it's not really straight, but approximately, we should do it this way around. It's approximately 7.2 centimeters long. So this is the cooling fan. This is the heatsink with a small, 30 millimeter cooler on top. And again, this thing can dissipate between 25 to 30 watts of power. And that's what I meant if you compare to the other ones, a heatsink. No, let me grab the heatsink. Now this is approximately how a standard heatsink from Intel looks like. It's not actually one, I don't think so. It could be, but I don't remember. But that's approximately the size you would get from one of these commercial units you can buy from China. The heatsink they use for a 60 watt unit, and this one is really big. It's 9 centimeter diameter. It has a thickness of almost 2 centimeters. So I mean, it's not bad. With this cooling solution, obviously the components, they do get hot. I mean, I'm running this at, I think, 70 degrees Celsius, maximum 75, and it's not a problem for the IR 540. The only thing is the cell gets a bit hot, so I tend not to use it at its maximum capability. But that and bigger heat sinks are just a waste. So, if you, well, okay, so for 60 watt version, that's too small. That would be fine, but sometimes there are massive heat sinks installed, and they are really a waste. Because heat sinks, they are expensive, and yeah, just something to look out for, and this should give you an indication what you need. This is, I would say, the minimum requirement of cooling. You can always make it bigger, and if you don't mind, you can oversize it massively. it's just unnecessary, and heat sinks like this one can be used for other projects. It's just a cost-saving measure, and it's not really that the components will die quicker. The IRL 540 has a maximum, I think it's junction temperature of 175 degrees Celsius. So on its own it could be run at I think 150. Junction temperature essentially means the internal temperature, if I remember correctly. So it's not the actual maximum outer housing temperature. However, you can calculate that. You get the thermal conductivity of the IRL 540's housing material, and then you can use the junction temperature to calculate what the maximum actual heat is it can handle, because you also have the rating for its maximum power output in heat. But that's just something to consider. You don't have to resize it. And before I end the video, let's just power it on quickly and make a small test so you can see that it really can do what I claim it can. Okay, before I close it up, just one more thing. I now attached a temperature probe at the heatsink on the end over here. This is the best point I can measure temperature. Obviously, temperature over here will be slightly higher than over here, but that's not a big deal. And we can see how hot it actually gets if I reach 30 watt of power, because today I think it's cool enough for maybe not. We have currently 27 degrees Celsius ambient temperature. At 30 degrees Celsius ambient temperature I would not exceed 25 watt of power, and I would like to have more like 24 degrees Celsius ambient temperature for the maximum 30 watts of power. Just something to keep in mind. We can start the test. We're currently at 27.1 degrees Celsius heatsink temperature, and if I now also turn on the fan, okay, we are at 5.03 watt on my bench power supply. Supplied voltage is actually 4.99 volt at 1.01 amp. So temperature rises, which is to be expected, and everything's under control. But now let's go all the way up to directly 5 amps, so we don't waste any more time. I think 25 watt should be achievable today. And we are at 25 watt of power displayed on my power supply. Well, obviously I'm currently using cables that are 1 meter long, so we lose a bit of power, but that shouldn't be a problem. However, I could make it a bit higher. Let's go to 25.5 watt, so we account for the power loss in the cable. I don't expect to lose more than that. And as you can see, temperatures are still in control. However, they climb faster, and that is to be expected. If you waste more power across the IRL 540, it will climb even faster. And that's another very interesting thing to consider. If you build one of these and you have a good power supply, you can actually also rate your electronics load for higher currents, or rather higher power consumptions, for short term. For example, this thing, I use it for up to 10 amp for 5 minutes, but at a relatively low voltage at only 5 volt, so it was 50 watt of power for only 5 minutes, and that's not a problem. That's also very interesting. So you don't only rate your power supply for maximum power consumption, for maximum current, but you can also rate it for short-term burst power consumptions and stuff like that. And as you can see, temperature climbs up, and I will come back to you as soon as we reached equilibrium. this should give you an indication on what you need to do for cooling. And I hope you liked this video, and if you did, please leave a like, comment down below. And other than that, thanks for watching and see you next time. Bye. And just before I end the video, a quick preview on my next DC Electronics Load project. We have bottom layer and the mirrored top layer for the PCB that I'm going to etch. And this will be a bigger version that actually consists out of 4 times this part over here, and this is essentially just this part 4 times mirrored and in parallel, bottom layer, top layer. And I will go in detail more once I actually start the project, and there will be a video about etching a PCB beforehand, because I think it's a very interesting thing, etching your own PCBs. I haven't done much on my own custom PCBs, but I would like to try a few things, and hopefully this will be very interesting, as well as the actual video in which I will build the bigger version.